In this video, we'll talk about the conservation of momentum. This is one of the major conservation laws in all of physics. It's actually even more relevant than the conservation of energy. We all know, I think, about the equation E equals mc squared, and what the equation says fundamentally is that the that mass and energy can convert into each other. It took Albert Einstein, to find that out, but we know that now. So one of the things that really threw scientists when they're looking at some of the first particle collisions is that mass would seem to disappear, or energy would seem to kind of leave the system for no reason. And so, that strictly speaking, the conservation of energy is the conservation of energy and mass, put together. But this conservation of momentum, we really haven't found an exception to this yet. And the other good news is that, in my opinion, this is actually easier to use than the conservation of energy. When we use conservation of energy, we have to decide, okay, what types of energy do we have beforehand? What types of energy are in a system afterwards? What work, was done on our system? So there's kind of more to it. With conservation of momentum, as you'll see, it's very simple. We just have to calculate the momentum of the system before, calculate our momentum after, and as long as there's no external force that causes an impulse, then that momentum for the system will stay the same. So if you had to put this in words, we would say in the absence of an external net force, the momentum of a system will remain constant. And the way that this translates mathematically is that the momentum of the system before has to equal the momentum of our system after. Now, you have to be careful when you use conservation momentum, because although you don't have to identify different types of momentum, remember this is a vector quantity, and so we have to set a direction. So, for instance, if I had, I'm going to call this object A, if I had object A here, and I had, object B right here, and this had some mass ma, this had some mass mb, and for some reason this was my system, and these two, maybe the explosion occurs or something inside of our system, so we say our system is these two objects in here, and this might be my before, right? And if they're not moving, there's no momentum. Okay, simple enough. Now say that something occurs inside the system, and object A starts moving this way, and object B starts moving this way. Okay, I'm going to call this velocity VB. I'm going to call this velocity VA. With momentum, we have to make sure we take into account the vector nature of this. In other words, one of these is going to be positive and one of these is going to be negative. So we have to set our positive direction, and that's up to you, but we'll say that way is positive maybe. And so what we would say is that since our momentum before, so this is our after, okay, so this is our after, and we would say that putting this together, since our momentum before was 0, we would say 0 kilogram meters per second is going to be equal to the momentum of A after the collision plus, explosion, plus the momentum of B after the explosion. And this in turn will be the mass of A times velocity of A plus mass of B times velocity of B. But one of these is going to be negative. So if when we plug in numbers for this, if we make that positive, then this is going to end out to be negative because I have to add these two together to get 0. So one of these is going to be a negative quantity. To help you kind of see how this works a little bit more easily, we're going to look at a sample problem. Okay, so there's typical problems that come up when we talk about conservation momentum. Explosions and collisions are probably the most popular ones. So in this problem, we have an explosion. We have a canister, and it explodes into two pieces. Okay, so our before on this will just be the canister at rest. It's going to have a velocity of 0 meters per second. Okay, and then afterwards, one of these pieces, so explosion occurs, and one of these pieces is going to fly up this way to the north, at 100 meters per second, and this is going to be our 50 kilogram piece. And then the other will be going south. Okay, and we know that the mass is 40 kilograms, but we don't know what that velocity is. So using the conservation momentum, this idea that the momentum before has to equal the momentum after. My momentum before, because my velocity is 0, once again, is just 0 kilogram meters per second. My momentum after, I'm going to choose up as being positive, so I'm going to say that this is 50 kilograms times 100 meters per second. So this is the momentum of the part of the canister going up. And remember, since this is our system beforehand, both these are still included in our system. So this will be the momentum of this piece plus the momentum of the piece going down. So this will be 40 kilograms times its velocity. That has to equal 0. And if we solve for this, this is 5,000 kilogram meters per second plus 40 kilograms times v. So we subtract 5,000 from each side, kilograms meters per second. That has to equal 40 kilograms times v. Solving for velocity, we get a negative 125 125 just meters per second. And again, all this negative is telling us is that this is traveling down. Since I defined up as positive, down is going to be negative. And so that has to be the velocity of the piece traveling down. Okay, which I think is pretty cool. The fact that we can use the idea that our momentum has to be constant to solve for the velocity of that piece. Here's another one. It's not an explosion in the traditional sense, but we have an astronaut and they're on a spacewalk, right? And oh no, the tether breaks. Okay, there's no way to haul them back into the ship. And so we don't want them to die in deep space. So what the astronaut, being the intelligent person they are, they decide to throw the wrench that they're holding in the opposite direction away from the ship. So you imagine, kind of our before, we have our astronaut, they have a wrench, okay? And then maybe our spaceship is right here. Okay, so there's a spaceship. And what they're going to do is they're going to throw it they're going to throw it away from the ship. So they're going to throw it in that direction. So after, we'll have our wrench traveling in this direction, and our astronaut is going to save themselves and travel in that direction. And so the question that you're being asked is, how fast will that astronaut be moving? Well, once again, our system isn't going to include the spaceship here. It's going to be astronaut plus the wrench. Okay, so originally they're both at rest. And so once again, we'll have velocity is equal to 0 meters per second. This doesn't have to be true, guys. We can have a velocity that's not 0 initially, but it does happen a lot. And then afterwards, so this will be our initial momentum, right? Whatever the mass is times the velocity, that's going to be 0. And then we have to define a positive direction. In this case, I'm going to define positive is to the left because that's where the wrench was thrown. So the wrench is traveling, it has a mass of 1.5 kilograms. It's traveling at 15 meters per second, which is it's a little over 30 miles per hour if you're wondering how fast that is. Plus the mass of the astronaut, so this astronaut is 55 kilograms, times the velocity of the astronaut. Okay, so once again, we have this case, this will be negative 22.5 kilogram meters per second plus 55 kilograms times v, and then we solve for v. I'll let you guys do the algebra on that. But we solve for v, and we get negative 0.41 meters per second. So it's going to take them a little bit to get back to that ship, probably. But they will get back to the ship, and they'll be saved, and everyone will celebrate. So this negative, once again, means that the astronaut is going to travel in the opposite direction from positive. So these are two examples, kind of exploding examples. We'll do other examples in class and on the worksheet, but the idea with all of these is you have a before, you have an after, so it's kind of like you have two diagrams. You calculate the momentum, you define your system, you calculate the momentum before, You then calculate the momentum after. So this can be like the sum of all the pieces in our system. And those two sides have to be equal, which allow you to calculate things such as velocities. If I gave you velocities, you could calculate mass possibly. So anyway, we'll do more of this in class. And if you guys have any questions, please let me know.